Welcome to our last lecture for our lecture series, Demography Today, sponsored by the BBVA Foundation and co-organized by the Spanish National Research Council and the LOMPOP Horizon 2020 project. And to finish our lecture series, we have the pleasure to have here Gerardo Chowell. He is a second century initiative scholar and professor of epidemiology and biostatistics at Georgia State University in Atlanta. He is also senior fellow in the Division of International Epidemiology and Population Studies at the Fogarty International Center from the National Institute of Health. Dr. Chowell holds a PhD in biometry from Cornell University. After obtaining his PhD, he was awarded a director's funded postdoctoral fellowship to support his mathematical modeling research program at the Theoretical Division of Los Alamos National Laboratory. Dr. Chowell's academic career has primarily focused on the development and calibration of mathematical and computational models of infectious diseases transmission to assess the transmission potential of emerging and re-emerging infectious diseases, and generate disease forecast, quantify the effect of control interventions, and test public health policy. He is currently a member of editorial boards of several key journals in medicine and epidemiology and mathematical science. So for us, it's a great pleasure to have him here. We have quite a wide collaboration with the Fogarty International Center and with Gerardo Chowell in particular on our projects. We will be doing this in the future. So this is a good opportunity to have you here and just to see the work that you are carrying out. So as usual, we have around 1 hour or something like that for the presentation, and then we will open the floor for questions. So welcome again.
Okay, so today I will talk about some of the work that we have been conducting over the last 4 years, particularly on trying to develop new methods to model infectious disease transmission and to generate useful forecasts of disease incidents. And I will present a couple of examples, particularly on Ebola and Zika, although I also have a more recent example based on using data from the 2001 foot and mouth disease outbreak in the UK. So to start, I will give you a little bit of background to be sure that the key concepts are covered. To start, the basic reproduction number, which we denote as R0, this is a key quantity in infectious disease dynamics because it quantifies the average number of secondary cases that an infectious individual generates in the community during his or her infectious period. Okay, so if I'm sick with the flu, how many cases on average I would generate in a completely susceptible population? For flu, that can be on average around 1.3, 1.5. Okay, so that's just an average. For pandemic influenza, that could be anywhere between 1.8 to all the way to 4, for instance, depending on whether we are talking about transmission at the community level or hospital level or confined settings. So if R0 is less than 1, we expect that the disease will not be able to generate a substantial outbreak, okay? Because it cannot really sustain, the pathogen cannot really sustain itself in the population. But if R0 is greater than 1, then of course we can expect that an outbreak will occur and could generate substantial morbidity and mortality unless we put in place interventions and control measures. So for public health authorities, it's very important to quantify with uncertainty, the value of R0 for any new outbreak, because that will define or help determine the type of interventions that need to be put in place and the intensity as well of the interventions. So the greater R0 is, the more intense interventions we need to put in place, and also consider possibly a range of interventions, not only one single intervention, but a combination of them that may include pharmaceutical interventions such as antiviral treatment, vaccination, if a vaccine is available, or even promoting hand hygiene in a community, okay, and behavior changes in the community to reduce their contact rates. So this is an example where we have R0 equals 2. So the infectious individual generates 2 secondary cases, and then the new secondary cases, each of them generate 2 secondary cases. So this is just an example where R0 is 2 for every single infectious individual for just a few chains, a few generations of transmission. And on the right, we have a population that has been previously exposed to the disease. So those circles in yellow are partially protected. So in this context, we talk about R rather than R0 to ensure that we understand that we are working in the context of a population that has been previously exposed to the disease, or perhaps even has been immunized previously. Okay, so we have a partially protected population in this setting. Another concept is the generation time, which is also a key concept in demography, right? The generation time is the time that elapses from the appearance of infectiousness to the appearance of infectiousness in the secondary case that a primary case generates. Okay, so the time that elapses from one case to the next, it's what we call the generation time. And in this example, we have a transmission tree where R0 is 3. So this primary case generates three secondary cases, and then each of these 3 secondary cases in turn generates 3 secondary cases. So in this case, R0 is fixed at 3 for this example. Okay, so let me start giving you a little bit of background on the Ebola, particularly the recent outbreak in West Africa that affected greatly the countries of Guinea, Sierra Leone, and Liberia during the years of 2014-15 for the most part. So Ebola is a virus that can generate outbreaks in the community. Typically, these outbreaks start when a susceptible individual is in contact with the animal reservoir that is that has been hypothesized to be primarily in fruit bats. Okay, but Ebola can also affect other animals such as non-human primates. So when a susceptible human, let's say, plays with fruit bats or eats a soup of fruit bats, then they are at risk of getting infected with Ebola virus. Then we have a new infectious individual that can generate secondary cases at the household level, right? Because the individual will be sick, will be shedding virus, and other susceptible individuals in the home may take care, right? Likely will take care of the sick and get in contact, and they get exposed to the virus. Now that infectious individual may go to the clinic, to the hospital, and also generate secondary cases unless strict infection control measures are put in place. There is a high risk for nurses and healthcare workers, right? And even when they are using face masks and gowns, any little error could actually lead to infection. And we saw that in the United States with a couple of nurses getting infected in Texas, right? You probably heard of that case, those cases. Another possibility is that once if the individual dies, cultural factors play a role. Particularly in West African communities, individuals tend to mourn, right? Mourn the death and spend a lot of time with the dead, touch the body, kiss the body, sleep with the body. So that, you would imagine, increases greatly the chances of passing the virus to other susceptibles, and many of them. And during the funeral settings, you can have not only family members in the same community, but you have family members coming from different communities, surrounding areas that can actually lead to new infections in new communities. And that's how Ebola actually spread in West Africa in 2014. Okay, so one of the main messages that I want to drive home is that it's very important to understand whether an infectious disease outbreak is growing in an exponential fashion or it's growing in a particular polynomials of exponential fashion. You are aware that in many fields, not only in epidemiology, but also in demography, in physical science, and we often make assumptions, and we often like to assume that things grow in a particular way because perhaps we have methods that are available under those assumptions. And if we are not very careful in making sure that the assumption is met, then we can get in trouble and generate wrong forecasts, wrong predictions, inaccurate predictions. So this is just an example to show you examples of cubic growth, fifth growth polynomial, 10th growth polynomial, and exponential growth. Okay? So exponential growth, it's the type of growth that you can get when the growth rate, the intrinsic growth rate, is maintained constant. So there's no change in it. But if the intrinsic growth rate is actually changing, declining, then you can have a polynomial sub-exponential type of growth. Okay? So this is just for visual representation. This is the type of exponential growth that you will have in a transmission tree. So everything starts at the center. You see how quickly the number of cases grows in just a few generations. This is an example with sub-exponential growth. Okay? So also visually, if we have the trend of growth in number of cases or population size, we can look at the graph in log scale, right? This is cumulative number of cases. And if in log scale we see a straight line, that is indicative of exponential growth, right? So we look at the graph and we say, okay, this is roughly exponential. But if we see that there's some curvature, like in here, in these graphs below the exponential curve, that's indicative of sub-exponential growth, polynomial growth. And therefore, in that situation, we're interested in knowing whether, whether this is a cubic polynomial or fifth growth polynomial, right? And making the assumption of exponential growth wouldn't be appropriate, right? The field of infectious disease modeling has made this important assumption that epidemics grow exponentially at the beginning unless we put in place interventions, right? Unless a substantial proportion of the susceptible population declines, okay? So that's something that is important to keep in mind. One of the very first epidemiological transmission models that were introduced by Ross and Kermack and McKendrick is the famous SIR transmission model. So S stands for susceptibles, I for infectious, and R for recovered. So susceptibles in contact with infectious individuals will generate more infectious individuals, right? And infectious individuals recover at some rate, okay? So this is what we call the compartmental model. Susceptibles progress to the infectious compartment. Infectious individuals progress to the recovered compartment. Beta typically is the Greek letter that we use to denote transmission rate, and that is given by the product of the contact rate and the probability of transmission per contact. So that will depend on the type of disease. And R0, right, the basic reproduction number, is given by the ratio of beta and gamma. Okay, gamma is the recovery rate. So this is essentially the product of the transmission rate and the infectious period, which is 1 over gamma. The infectious period will give us the window of opportunity that infectious individuals have to generate secondary cases, right, during the period of infectiousness. So this model is the building block for more complicated, more complex models, more elaborate models of transmission that, as I was telling you, assumes that the number of cases of disease will grow exponentially unless interventions are put in place or unless the susceptible population declines substantially, right? But this assumption of exponential growth didn't really apply for the Ebola epidemic. We start looking at the early chains of transmission that were reconstructed. We see that the index case was traced back to a 2-year-old child that was playing with some fruit bats with other kids. This child unfortunately got infected, passed the disease to her mother, to her sister, to his sister, and then there were relatives getting infected and healthcare workers and nurses. But for the most part, the transmission chains was spatially constrained. So it's not that the child was starting to generate chains that were going far away from the town where everything started in Gekedu. But it was more a spatial wave of disease that was moving from Gekedu into other districts, neighboring districts, and then eventually to other countries as well that are very, very well connected to Guinea, particularly Liberia and Sierra Leone, as you can see. So the assumption that the disease will spread homogeneously in the population didn't really quite apply here. Another important aspect of Ebola is that it spreads really by close contact. So it requires some intimate contact between the one that is sick and the susceptible. It is not an airborne disease like influenza. Otherwise, we will have a different story right now, right? And really spreads among caretakers particularly at home or at the hospital setting. This graph here shows the viral load, the typical viral load for an infectious individual with Ebola. So the viral load peaks around day 5 after exposure. And typically at that point, the person is so sick that is confined to her home or in the hospital. So it is unlikely that individual will move around and spread the disease far away. If we look at the epidemic curves for past epidemics, past outbreaks of Ebola, we see that these curves were characterized by rapid growth, but just short and rapid growth. As you can see here, this is the first outbreak that was reported in Congo in 1976. This is Congo in 1995, Congo 2014. Indeed, this was a parallel outbreak to the one that was unfolding in West Africa. But you see that all of these outbreaks are characterized by this short period of rapid growth and rapid saturation in growth. So the outbreaks really quickly end after just a few generations of transmission. And it is likely that the reasons for these outbreaks ending so early is that individuals in the community realize that there is a pathogen that is spreading and is generating severe disease and death, that individuals quickly learn about that and they change their behavior, okay? They reduce their contact rates, and that's really what leads to the ending of these outbreaks. During the Ebola outbreak in 2014 in West Africa, this is the type of epidemiological data that was available. It was very limited. This is in blue the curve of cumulative cases in Guinea, in green for Liberia, and in red for Sierra Leone. As you can see, when we started to look at these curves in Guinea, for instance, this growth here was roughly linear, if you want, which can be consistent with exponential growth, right? So that was the scary part, that if we start to look at this curve, it was growing exponentially. And then Liberia later on started to report cases and observed a small wave here and then a second wave here. So this is about the time when public health authorities thought that the epidemic was getting under control, but it wasn't. And the problem was that the surveillance system were not really strong to be able to provide the real picture of the outbreak in West Africa. Now, if we aggregate all of these curves together, this is the epidemiological curve for the entire West Africa. We see here Again, this exponential growth, just because Guinea had some apparently exponential growth during this early phase. But the problem is that there was no data about what was going on at the district level, right? So I was showing you the transmission trees in Gekedu, the town where the transmission started, but we didn't have number of cases, the time series of cases at the district level to be able to understand better what was going on in each of these 3 countries. Later on, actually close to the peak of the epidemic of Ebola, this data became available, and it became really clear that the outbreaks at the local level, at the district, subnational level in West Africa were not growing exponentially, but were actually showing clear signs, very quickly clear signs of sub-exponential growth. Even in the town of Gekedu, right, where everything started, we see a curvature in this curve in log scale, indicative of sub-exponential growth dynamics, even before the outbreak was notified to the World Health Organization. Okay, so this data could have been very helpful to better validate transmission models that were being developed by a number of modeling teams in the international community. And also at the same time, notice the outbreaks, the curves are not occurring really starting about the same time, but there is a sign that the epidemic was spreading in a spatial wave fashion, right? So you see all of these curves are really asynchronous in time. So it was moving spatially across the 3 most affected countries in West Africa. And this was a bit reminiscent of what happened during the early years of the HIV/AIDS epidemic. And this is data for the United States. And back in this PNAS paper in 1989 reported that the growth in the number of, the community number of cases of HIV/AIDS in the US was growing more like a cubic polynomial, okay? Which is consistent with what we are seeing for Ebola. Both diseases are transmitted through close contact, right? They are not transmitted through the air. And even when the data was stratified according to race group, even for different geographic regions, the data is not here, the epidemic curves show a cubic polynomial growth approximately. So what mechanisms can give rise, right, to sub-exponential epidemic growth patterns then? So then we started to think about what are the main mechanisms that can explain the patterns that we were seeing in the Ebola epidemic. One of them is reactive behavior changes. So people in the communities quickly react to the presence of the disease, and they change behavior, they reduce their contact rates, and they take action to avoid getting infected, right? Not only them, but also their families, right, their loved ones, and their communities. Non-homogeneous mixing, right? Homogeneous mixing is the central assumption in the building block of SIR models. But we need models that assume something that is not homogeneous. So that would include models that incorporate a particular patterns of contact that will not assume that everyone can be exposed to Ebola in a particular population. And one type of non-homogeneous mixing is spatial structure. And I'll show you some examples where the disease can spread, where we can actually model spatial spread of disease. So these are the 3 main mechanisms that we identified that could explain the sub-exponential growth patterns. So let's start with reactive behavior changes. So let's look at the simplest model that can give us this type of dynamic. So it's this SIR model that I showed you earlier, but now the transmission rate actually declines exponentially fast. So this is my transmission rate. It's a function of time. Beta 0 is my baseline transmission. But then now this beta 0 will decline according to this exponential function, okay? And will decline such that asymptotically the reproduction number will reach 1. Okay? So if this Q rate here in the exponent is 0, we go back to the homogeneous mixing assumption, right? If Q is 0, this is just beta 0, right? So constant transmission rate. If Q is a bit greater than 0, like in this graph, it's clearly showing that, then we have the decline in the transmission rate. And what we see is that from having a straight line, right, in the log scale for Q equals 0, exponential growth, with a small increase in Q, 0.05 for instance, we quickly start to have this type of curvature away from the exponential growth pattern, right? And as we increase, of course, Q, the decline in the transmission rate will lead to this type of patterns that we observe in the empirical data sets. And then the corresponding curves for the changes in the reproduction number, the effective reproduction number. So the effective reproduction number is tracking how the transmission potential or the transmissibility is changing over time. You see that in the case of exponential growth, we expect to have a sustained reproduction number, right? But as soon as we start to increase the Q parameter, we see that the reproduction number actually declines, okay? And that's consistent with the polynomial type of growth in the epidemics. What about non-homogeneous mixing? The same model, SIR, we start with the same SIR type model, but now we use this type of exponent alpha that is a power of I. I is the prevalence, right? The number of infectious individuals in the community at time t. Now, if alpha is 1, then we just get the same exponential growth dynamics, right? Because we go back to the simpler, this is the baseline model. But as alpha goes below 1, now we are modeling something that is not mixing directly, homogeneously, but we are modeling in a phenomenological way transmission in a non-homogeneous fashion, okay? So as alpha goes below 1.0, we see that incidence starts to show the pattern of polynomial growth, right? And the same thing for the reproduction number, the declining trend in the reproduction number over time, okay? What about the spatial structure? So we can think of a community like, or a population like this one as a square lattice. So each cell, each square here is one individual. And this red cell is the start of the outbreak, so one infectious individual. And then this column here corresponds to the household where this individual lives, okay? So this individual may transmit the disease to any of these individuals in this household, and with a lower probability could transmit the disease to a number of households within the community. So the gray area here would correspond to the community in which this particular household belongs to. So the community is basically a number of households to the right and to the left of this community, okay? So you can pick any household, and for that particular household, you have a range to define the community, okay? So the individual may transmit with a probability within household, but also within the community. And we can get this type of simulation where you get high transmission within the same household, and then start to spread with a lower probability within the community. And then this is at day 21, at day 42 of the simulation, and day 63 and 74. So you see clearly that the disease is actually spreading in a wave fashion, right? It's not affecting everyone at the same time, but it's spreading in a wave fashion, a spatial wave that is moving through the susceptible population. So with this type of model that is still simple enough, we can recover the type of a spatial dynamic that can lead to non-exponential growth, so exponential dynamics. Now, if I have the data, right, coming in for a particular epidemic outbreak, or we can also think of any type of process in demography, what type of model can we use? The question is, what type of model can we use to actually quantify from the data whether something is actually growing exponentially or polynomially? So we play with the generalized growth model, which actually had not been used in empirical settings. It had been described in the mathematical literature. And the generalized growth model is similar to the exponential model, except that we have this exponent p, okay, affecting the cumulative number of cases c. Okay? So if we remove the p, you may be familiar with the exponential growth equation, right? The Malthus equation that was used to describe the early growth of the population of the world, right? If we put the p here, and p is confined within the range of 0 to 1, of course, if p equals 1, then we go back to the exponential growth case. But if p is less than 1, then we have polynomial type of growth, okay? And the lower the value of p is, the slower the type of growth, right? So we move away from the exponential growth dynamics. And if p, another special case is p equals 0. If p equals 0, then this describes constant growth, right? Something very simple. So something that is, let's say, X number of cases are occurring every day, constant, okay? So we can use this model to quantify the value of R, which is the intrinsic growth rate, and most importantly, P, which is the parameter that defines the scaling of growth for a particular process, and statistically estimate the parameters with quantified uncertainty. This is an example of the type of simulations that I was just describing. If P is 0.2, 0.3, and 0.4 right here, basically if P is less than 0.5, you get this type of curves that are concave up, right? In mathematics, this type of curve is concave up. If P is greater than 0.5, you get a concave down curve. If P is 0.5, actually, you get this type of linear trend, okay? Now, importantly, small changes in P, so if we move P within a small range, let's say from 0.46 to 0.62, you get high variation in the outcomes. So for instance, let's pick the cumulative number of cases at day 100. You see that we see a lot of variation with small changes in P, okay? So that highlights the importance of being able to quantify the uncertainty in these parameters, right? Whether P is between 0.8 and 0.9, or it's actually all the way to 1, and understand whether this growth profile includes the possibility of exponential growth. Because if my parameter P, let's say my confidence interval is between 0.9 and 1, that will include the possibility of exponential growth, right? And we can include that in our predictions and estimates. So we use this model to test it with empirical data from different outbreaks, ranging from pandemic flu, smallpox, plague, HIV/AIDS, measles, and a bunch of Ebola outbreak data that we were getting from the 2014 Ebola outbreak in West Africa. So we got this data, we fitted the model, the generalized growth model, and then we compared the fit with the exponential growth model, which has been the classic model for the early growth of epidemics. And what we found was that the generalized growth model, of course, was giving a much better fit to the data, even for cases where the dynamics are very close to exponential. The generalized growth model was giving a much lower error in the fit to the data. You see, for instance, this case for the HIV epidemic in Japan, we see clearly that the exponential growth model doesn't work at all, right? Even for Ebola, this is Ebola in Western area urban, which is the urban area of Freetown in Sierra Leone. We see that the exponential really fails to capture the sub-exponential pattern in the data, and we see that the errors, the sum of square errors, are much lower for the generalized growth model. And so this highlights the importance of capturing better this early growth profile, because that's the type of information that we use to estimate the reproduction number and the basic reproduction number. And also, if we are able to better calibrate this part, we should be able to provide more accurate forecasts, right, that reflect what happened in the past. So we analyzed a number of data sets. This is HIV/AIDS in Japan, the one we're just showing you, western area and urban area. This is Liberia and Montserrado, where there's a high uncertainty, as you can see here. The uncertainty in the P parameter, using only a few data points, it's quite high. But as we use more and more data, we get a better range of the P parameter, right? So not surprisingly, if we have very few data points, it will be hard to say whether something is growing exponentially fast, right? If I have only 2 data points, well, I can fit anything, right? Any function I can fit to 2 data points, a line. That would be the simplest one. I can fit an exponential, yes, of course, but the uncertainty will be very large. This is another example where P is actually less than 0.5. This is Ebola and Kenema, Sierra Leone. Now, we put all of the P estimates reflecting the scaling of growth of these outbreaks, ranging from pandemic flu to Ebola. We see a lot of variability, right? And we see a lot of uncertainty as well. And that variability indicates that it's important to actually treat each outbreak. Even if we're talking about Ebola, each Ebola outbreak has different growth profiles that are far away from the exponential in most cases, and also have substantial uncertainty. So using this uncertainty will give us better footing on estimating the reproduction number and generating forecasts. So short-term forecast, what do I mean with that? Short-term forecast means I feed the model to some early data. So I have a few data points of the early growth of the epidemic, and I have a model, so I can fit that to this data prior to this vertical dotted line, right? Let's say 2 generations of transmission dynamics. And then I try to predict in the short term what's going to happen, right? If I have very little data, it will be very difficult, right, to know whether this is really growing exponentially or not. If I fit an exponential here, so what I will get as a forecast is something that will grow like this, exponentially, right? But if I use something that will treat better the uncertainty in this growth pattern through the pre-parameter in the generalized growth model, I could generate a more realistic forecast. Okay? Indeed, if we generate data, let's say this is simulated data from the generalized growth model, where P is 0.92, 0.94, 0.96, so clearly below the exponential growth regime. And then I take the exponential growth model, perhaps it's not surprising that the forecast will overestimate all of, in the short term, even in the short term, the data. Okay? So here, this is my data. This is my corresponding forecast for this data. So you can see clearly how we overestimate quickly. Now, if we let this forward, this exponential growth will be over here. The data will be over here. So the farther away we project our forecast, the greater the error, right? And so this is the calibration period. This is my forecast for these 3 different values of P. The closer we are to the exponential growth regime, perhaps the exponential growth model will do better in the short term. But even in those cases, the error in the long-term projection will also be significant, according to our simulations. Okay, so what are the implications of this on estimating the effective reproduction number, which gives us information about how the outbreak is evolving over time, changing over time? So if p equals 1, we knew that the reproduction number is actually a very simple formula. It's e to the r times tg. R is the growth rate, and tg is the fixed generation interval, right? But if p is not 1, is less than 1, if we are in this context of sub-exponential growth, actually the effective reproduction number is not a constant like in this case, but it's a little bit more complex. And in fact, this value, according to this formula, declines asymptotically towards a value of 1. So the reproduction number declines over time towards 1.0 in the sub-exponential growth regime. And we can compare the analytical results with numerical estimates using this also very well-known formula. This is the effective reproduction number. I is the number of new cases. And the denominator here estimates the number of cases that likely contributed to the number of secondary cases. So this ratio will give us the effective reproduction number. So this is an example where we have the data coming from the generalized growth model. So if p equals 1, we have this type of exponential, and then if p is 0.9, 0.8, 0.6, we have a slower and a slower growth, and the corresponding curves of the effective reproduction number are here. If we are here, the effective reproduction number is constant, right? But as soon as we go below 1, the effective reproduction number declines. It's lower and also declines over time. So it's really a dynamic quantity, right? Now, p is not telling us, right, any information about what is the mechanisms that is causing this type of sub-exponential growth. But I already told you earlier that you have these 3 mechanisms, right? A spatial structure, behavior changes, the role of intervention, non-homogeneous mixing, can all of those individually or a combination of them can lead to sub-exponential dynamics of growth. So now with this model, we can get more precise estimates of the effective reproduction number. And this is an example for the 1918 flu in San Francisco. As you can see, the effective reproduction number during the early growth phase is 1.8 using 12 data points. If we use a little bit more data, it's slightly lower, right? Because we know that over time, if we have something that grows polynomially, as I showed you earlier, will decline, right, towards 1. This is a more polynomial case, the foot and mouth disease in Uruguay, where the R is 2.8 during the first 7 days, and then as we move forward, the estimate goes lower, declines, and more, okay? This is an example with Ebola, where p is 0.5, so it's clearly a sub-exponentially growing epidemic. R is 1.3, and then declines here up to 1.2 when we use either 6 data points, 8 or 10 data points. And each data point is a week. Now we can put everything together, and we observe that the estimates of the effective reproduction number will tend to be smaller compared to those that we obtained assuming exponential growth, right? Which is not surprising. The exponential growth assumption will tend to overestimate our estimates of the reproduction number and also the forecasts of incidence. So here are some examples now incorporating these concepts into forecasts of epidemics. The foot and mouth disease in the UK, this is an example that we recently conducted. So as you know, this is in 2001. The first case of this major epidemic occurred was reported or detected on February 19, 2001. It led to the slaughter of many animals, more than 2 million cows and sheep. So it was a major intervention put in place in the UK. Cumbria was the most affected one, and the cost was enormous. Just during the period of the epidemic, this is the cost estimated at $8 billion pounds. Okay. So we use this generalized growth model to see how well it could forecast the epidemic data. And what I'm showing you here are forecasts using an increasing amount of data. So if we move from here to the next, we are using 10 more data points. Okay? So imagine that we have the first 10 data points of incidents coming in from the surveillance, and then we calibrate the model with these first 10 data points, and then we forecast what's going to happen in the future using this generalized growth model. So this is our, and the forecast is actually 10 days ahead. Okay? So this gray area is the uncertainty based on the model forecast on where the epidemic will go next. Okay? And as you can see, these 10 data points is very little amount of data to calibrate the model, but still we can get a range of where it's going to go. And indeed, what we see is that the data, right, the data, the number of cases are the blue circles, fall well within the 95% confidence band, which is defined by these dashed red lines. But on average, it tends to go up. So perhaps this suggests that there were some interventions that were actually having an impact, right? Now, if we move forward, and now we use these 15 data points. So we're using more data now, right? And then we forecast forward the next 10 data points. We see the model starts to do a much better job now, right? So we have more data. The model actually predicts the mean going through the data very well. Okay? So even this simple model could have been useful to get an idea of where the epidemic was actually moving. Now we use more data, we get also a nice forecast of where the epidemic is going, and again, and again, and then here we start to actually deviate because the peak of the epidemic is being reached, as you can see, right? And then again here, there are clearly signs that some data points are falling, right, below my forecast. So that's a good sign for the public health authority, because you would say, oh, look, actually we have good confidence that the interventions and everything that is being put in place in the field is having an impact and is reducing the transmission rates. Okay? So this model works very well for the growth pattern, the entire growth comprising the first 40 days of the epidemic foot and mouth disease in the UK. Now we can also look at the parameters, right, of R and P, those two parameters that define the generalized growth model. So if we look at this snapshot here, right, if we use only the first 10 data points, you see that the estimates of R and P have very wide uncertainty. Okay? Actually, this horizontal dashed red line is the confidence interval, and the blue is the empirical distribution for the parameters. So at this point, we cannot rule out the possibility of exponential growth, right? Because my P parameter includes this one clearly, right? But as we have more and more data, what happens is that my parameters get better and better constrained, and the model gets better constrained to the data, and then we get a better estimate of our P parameter, clearly now showing that the growth was following a sub-exponential trend away from 1, right, which would be exponential. So that's the key here, that the model is able to capture the sub-exponential trend, and it's useful to generate the short-term forecasts. Now, if we contrast the forecast with this model with the classic exponential growth, this is what you get. For the first two forecasts, it does not a bad job, but even in the second forecast, you see that it starts to deviate, right, from the data, quickly deviate from the data, and then the fit gets poor, right? The model is actually underestimating the data here. And of course, now in this snapshot is very bad, worse and worse, right? Now, what about Zika? Zika is a virus that has been spreading around the world. It seems that it was introduced in the Americas from Africa, and colonized, started to invade the Brazilian population first, and then started to move roughly northwards from Brazil to Colombia and Mexico, and even the United States in a few areas. It is a very important pathogen because it has been linked to congenital disease, right, in babies, and the most severe cases have been associated with microcephaly. There are still many questions surrounding the causes, the risk factors for microcephaly. It appears that most of those microcephaly cases have been clustered in the northeastern part of Brazil, and we're still trying to understand what happened there. If we look at some of the epidemic curves that were generated through surveillance data, this is a particular case of Antioquia in Colombia, where public health authorities put in place a robust surveillance system to try to keep track of the number of Zika cases in the numbers of confirmed and suspected cases. This is the epidemic curve that was obtained, that was recorded for the department, right, of Antioquia. It's a department. And you see this is from 28 December 2015 all the way to April 10th April 2016. So you see that it has a relatively brief period of growth. It peaks and declines, okay? But even by eye, you see that this trend is not exponential, right? Oh, this is not in log scale, okay? Exponential will be something like this. So here, the case for sub-exponential growth models can be made again, right? So what we did was to modify the classic logistic growth equation and include the p parameter, right? So if we remove the p from this equation, that's the logistic growth equation, right, that we learned in probably high school, where you have this type of growth, right? P equals 1 here, right? But if we introduce the p in the same way that we did with the generalized growth model, then we can still have this type of growth, but a slower early growth dynamics. So the lower the p, again, the slower the growth, right? And you can actually capture polynomial growth dynamics. So this is a good example where we can test the sub-exponential growth dynamics in a model that not only gives you the growth, but also gives you the entire epidemic curve, the peak and the size of the epidemic. So we can fit the model very well to the data, and the p-value is 0.6, so it's clearly growing sub-exponentially. The estimate of the reproduction number is about 2.2 if we use only the first 30 days of the epidemic. But because the epidemic is growing sub-exponentially, the estimate of the reproduction number will decline, right, over time. Now we do forecasts. We use the first 20 days of data. This is our forecast. So really, this is very little data to be able to capture the peak of the epidemic, right? But as we use more data, right, of the epidemic, we capture the uncertainty a lot of the data points. And of course, as we use more and more data, the model gets some relatively good forecasts. Okay, they are not great, but they are good and useful to estimate the size of the epidemic. To the point that if we compare the forecasts with the actual epidemic size, so the horizontal red line is the actual epidemic size in Antioquia of reported cases, and then these blue bars are the estimates of the size of the epidemic. Okay, so there's a lot of uncertainty, but this uncertainty always overlaps, right, with the actual size of the epidemic. Now compare this forecast with those obtained with a model that does not incorporate the sub-exponential growth pattern. And what we get is that you always underestimate the true epidemic size, and then you get too much confidence in your confidence intervals. So very small and very severely underestimating the size of the epidemic. Now we go back to the foot and mouth disease example, the 2001 foot and mouth disease in the UK. If we start doing the forecast around the peak timing, right? So I already showed you the forecast that we obtained using the generalized growth model, but now we use the generalized Richards model, the one that I just introduced you in the previous slide, right here. We use this model, then this is what you get. If we fit it to around the peak timing, you get a good forecast, short-term forecast, and then as you have more and more data, you do a relatively good job at getting the epidemic, where the epidemic is going next, okay? And as a summary, we can say that it's important to consider the possibility of sub-exponential growth in epidemic dynamics, because that has implications for estimating correctly the reproduction number from the early growth data, and also generating more realistic forecasts that are consistent with the current data. And the generalized growth model is actually a useful tool to characterize the type of growth patterns, and this can be applied not only in the context of epidemics, but also in the context of things that are processes that are generating some growth of some quantity, of some population. So it has potential applications in other fields, ecology, demography. One new result is that in the context of sub-exponentially growing epidemics, the reproduction number is not a constant quantity, but actually declines, and declines asymptotically, right? And approaches the value of 1. And for epidemics that really truly depart from the exponential growth assumption, the use of methods that have the underlying assumption of exponential growth dynamics will tend to overestimate, right? Overestimate my reproduction number and also the forecasts of disease incidence. And finally, acknowledge a number of co-authors that have contributed to this work, okay, including my colleagues at Fogarty International Center, NIH, Tulane University, York University, and more recently, David Chanafeld and others with whom we have conducted the analysis of the 2001 foot and mouth disease epidemic in the UK. Thank you very much. I welcome your questions.